Hello, in the previous clip we had started on doing control design and we had laid out the steps involved in doing control design. So, the first step was to convert time domain specifications on performance into closed loop frequency domain specifications, and subsequently to convert closed loop frequency domain specifications into open loop frequency domain specifications, then execute the design so that these open loop specifications are met, and finally go back to the closed loop system and check whether the closed loop specifications are met, and finally check if the desired time domain specifications are met. So, these are the steps in control design. So, we have to check both for closed loop specifications and for time domain response, because there are approximations that are made in going from time domain to frequency domain and from closed loop to open loop. We also discussed that in the interest of appealing to a broad audience, we cannot focus on any one kind of input that might be of interest to one specific community, and we have to decide on a particular standard input. So, we chose the step input as the one as a reference input, and the response to a step input, namely the step response, would be the one that we would be looking at to evaluate the performance and stability of our closed loop system. So, we assume that a typical step response of our closed loop system might look something like this, and we attached a few characteristics to the closed loop response, and one was the rise time, which was the time it took for the response to rise from 10% of its steady state value to 90% of its steady state value. Then there was the peak overshoot, and then finally the steady state error. And then we were confronted with a dilemma about how to translate these time domain specifications into closed loop frequency domain specifications, particularly because we have not yet designed the controller. Indeed, the controller is the one that has to give us these specifications. So, our transmission function T, which is equal to Cp by 1 plus Cp, is as yet undesigned, but yet we have to somehow come up with performance specifications in the closed loop frequency domain that give us these particular closed loop time domain specifications. To undertake this exercise, before even having designed C, we invoked the advantages that would accrue from the notion of dominant closed loop poles. So, we assumed that our closed loop system would have a pair of dominant closed loop poles regardless of whatever controller structure we might end up having at the end of the day, and with that assumption we could approximate our closed loop system to be a second order system. So, this is only an approximate relationship in order to allow us to translate the time domain specifications into corresponding closed loop frequency domain specifications. Subsequently, now that we have assumed that our closed loop system would look somewhat like a second order system, though it might definitely not be a second order system in practice, we could then use standard relationships for the rise time, the peak overshoot and the steady state error for a second order system, and translate the corresponding time domain specifications to the parameters of our closed loop system, namely the constant k, which is given, which is obtained from the specification of a steady state error ESS, the damping zeta, which can be obtained from the peak overshoot using this equation, and finally the constant omega n, which can be obtained from the rise time specification, and this rise time specification relates the rise time to the bandwidth of the closed loop system, and the bandwidth is related to the natural frequency omega n according to this particular equation. So, by using the two together, one can estimate omega n and fix all the parameters of this approximate model. Since we have decided to undertake design using Bode plots, we have to translate the closed loop specifications into corresponding open loop specifications. So, in other words, we should come up with the correct performance requirements on the loop gain or the product of the controller and the planned transfer functions that give us this approximate closed loop transfer function. So, the easiest to do is to come up with the value of the loop gain or the value of the controller transfer function times the planned transfer function at steady state for DC references, and that is given by C of J0 times P of J0. We know that our transfer function is given by C of J0 times P of J0 divided by 1 plus C of J0 times P of J0. Therefore, if we have specified the steady state error, then we know what value of k we should have, and we can show that this should therefore should be equal to 1 minus ESS. So, T of 0 should be equal, T of J0 should be equal to k, which in turn should be equal to 1 minus ESS from this particular equation, and from this we can work out that our the product of the controller transfer function, namely C of J0 evaluated at 0 frequency times the planned transfer function evaluated at 0 frequency should be equal to 1 by ESS minus 1. So, converting the closed loop specification at 0 frequency to corresponding open loop specification on C of J0 times P of J0 was quite straightforward, and this is what it is. Next, we have to also translate the other specifications, namely that of omega n and that of zeta, to corresponding open loop specifications. Now, here once again we shall make an approximation. We shall assume that in our effort to translate the closed loop specifications to open loop specifications, our DC gain k is very close to 1. So, there may be a small difference between the actual value of the DC gain and 1, but we shall assume that for all practical purposes it is equal to 1, and this is not an unreasonable approximation, because generally we desire that at least for DC references most control systems show as close to 0 steady state error as is possible. So, if we make this approximation, then our transmission function approximately would look like omega n square divided by s square plus 2 zeta omega n s plus omega n square. Now, if I were to write this as C of s times P of s divided by 1 plus C of s times P of s, then I can undertake the algebra, namely that 1 plus C times P times omega n square is equal to s square plus 2 zeta omega n s plus omega n square times C P. By simplifying this expression, I would get C times P to be equal to omega n square divided by s times s plus 2 zeta omega n. So, the open loop transfer function which gives us this approximate closed loop transfer function is given by this expression here. Now, we can use this expression to sketch the approximate Bode plot for our open loop system and use that to determine the gain crossover frequency and the corresponding phase margin. So, to remind you from the previous slide, we have the open loop approximate transfer function. This is not the exact transfer function because we have not yet designed the controller C. In order for us to get the approximate closed loop transfer function that we wrote out in the previous slide, the approximate open loop transfer function should look something like this: omega n square by s times s plus 2 zeta omega n. So, to draw its Bode plot, we have to substitute s is equal to j omega, in which case we would have Cp of j omega to be equal to omega n square divided by j omega times j omega plus 2 zeta omega n. We notice that there is one corner frequency at omega equal to 2 zeta omega n for this particular open loop system. So, this is the corner frequency, and we have an integrator also as part of our open loop dynamics. So, our Bode plot would therefore have a decaying characteristic and the slope would be minus 20 decibels per decade up to the corner frequency minus 2 zeta omega n, after which we would have the slope increase in its magnitude further, and it would reduce at minus 40 decibels per decade, because we would have another 20 decibels per decade contribution from this pole of the approximate open loop system, and this would get the magnitude characteristic to cross over at some particular frequency omega gc. How will the phase response look like? The approximate phase response. I want to emphasize that we have not yet designed the controller. So, we have not yet determined the exact transfer function C times P. All we are doing is coming up with an approximate transfer function that will allow us to get the approximate closed loop transfer function, which in turn was useful in transferring the time domain closed loop specifications to frequency domain closed loop specifications. So, the phase response for this transfer function C times p will start at minus 90 degrees because we have an integrator here. So, it will start at minus pi by 2 radians, and then it will reduce and it will asymptotically approach minus pi, and it never crosses minus pi. So, this is going to be the phase response, and at the gain crossover frequency we can evaluate the phase of this transfer function, and the difference between minus pi and this phase is by definition the phase margin. Now, what we are trying to see is whether we can relate the phase margin and the gain crossover frequency to the parameters omega n and zeta of our closed loop system. So, to determine the gain crossover frequency, by definition we have to set magnitude of Cp of j omega gc, where omega gc is the gain crossover frequency. By definition this should be equal to 1. If this is equal to 1, then of course 20 log of magnitude of this would be equal to 0 dB, and then we would have the gain crossing over the frequency axis in the Bode plot. So, if this has to be true, then substituting it in the expression for C times P, we would have omega n square by j omega gc times j omega gc plus 2 zeta omega n magnitude should be equal to 1. So, you can solve this particular algebraic equation for omega gc, and you would get omega gc to be equal to omega n square root of 1 minus 2 zeta square. So, we see that if we have identified omega n, and this can be obtained from the rise time specification in the time domain step response of our closed loop system, and if we have determined zeta, which can be obtained from the peak overshoot specification, we can determine therefore the gain crossover frequency of our open loop system to be equal to approximately omega n times square root of 1 minus 2 zeta square. We can, now that we have identified the exact gain crossover frequency, we can also estimate the phase margin, because the phase of this open loop system, the approximate open loop system, would be given by the phase of the integrator, and the phase lag of the integrator is a constant at all frequencies, and that is equal to minus pi by 2, and the phase lag added by the other pole at s is equal to minus 2 zeta omega n, and that phase lag will be equal to minus tan inverse omega by 2 zeta omega n, where omega is the frequency at which we are evaluating the phase of that transfer function. Now, we know that we have to evaluate it at omega gc in order for us to extract the phase margin. So, the phase of C times P is given by this expression, and the phase of C times P at omega gc is therefore given by minus pi by 2 minus tan inverse omega gc by 2 zeta omega n, and that in turn is equal to minus pi by 2 minus tan inverse square root of 1 minus 2 zeta square divided by 2 zeta. I get this expression by plugging in the expression for omega gc from here. So, the angle of C times P at j omega gc is equal to minus pi by 2 minus tan inverse of square root of 1 minus 2 zeta square divided by 2 zeta, and I use the identity that tan inverse of square root of 1 minus 2 zeta square by 2 zeta is nothing but pi by 2 minus tan inverse of 2 zeta by square root of 1 minus 2 zeta square. So, this is a standard identity from trigonometry that I am employing, and if I were to do that and plug this identity into this particular equation, I would have angle of Cp at j omega gc to be equal to minus pi by 2 minus pi by 2 minus tan inverse 2 zeta by square root of 1 minus 2 zeta square, and that is equal to minus pi plus tan inverse 2 zeta by square root of 1 minus 2 zeta square. From the previous slide we have angle of Cp at the gain crossover frequency to be equal to minus pi plus tan inverse 2 zeta by square root of 1 minus 2 zeta square, and by definition of phase margin we know that the angle of Cp at j omega c omega gc is by definition equal to minus pi plus Pm, where Pm is the phase margin of our open loop system. So, by comparing these two equations we note that the phase margin is given by tan inverse 2 zeta by square root of 1 minus 2 zeta square. Therefore, we note that if we were to specify the damping coefficient for our closed loop systems zeta, which we in turn extract from the desired peak overshoot MP, we are effectively specifying the phase margin of our system. And a couple of clips back we discussed that the phase margin is a measure of stability of our closed loop system, and it is the maximum permissible phase lag that our controller can potentially add before destabilizing the system. So, therefore, specifying the closed loop damping, or in other words equivalently the maximum overshoot in the time domain, is equivalent to specifying a desired stability margin for your closed loop system. Now, we can simplify the expression for the phase margin further by noting that if the damping coefficient zeta is much less than 1, then in the denominator of this function tan inverse 2 zeta by square root of 1 minus 2 zeta square, the term 2 zeta square would be much less than 1. And what that would mean is that square root of 1 minus 2 zeta square would approximately be equal to 1, so that the phase margin would be approximately equal to tan inverse 2 zeta, and if zeta is much less than 1, we know that tan inverse of theta is approximately equal to theta in the limit theta is close to 0. Therefore, we can make an additional approximation that the phase margin is approximately equal to just 2 zeta. So, this fairly simple expression allows us to very quickly compute the phase margin of our closed loop system in radian if we have specified the closed loop damping coefficient zeta. Now, what is often done when we do control design is to represent the angles not in radians but rather in degrees. So, if one were to represent this in degrees, then one would have the phase margin to be equal to 2 zeta times 180 by pi. This is in degrees, and we note that 2 times 180 is 360 and the value of pi is 3.141, and therefore, the phase margin is going to be equal to 360 by 3.141 times zeta. This can be simplified a little bit further to make it easy for us to remember quickly what the relationship between the phase margin and zeta is going to be, by noting that 360 by 3.141 is approximately equal to 100. So, therefore, the phase margin is approximately equal to 100 times zeta when the phase margin is represented in degrees. So, therefore, we have now managed to successfully convert the closed loop frequency domain specifications into corresponding open loop frequency domain specifications. In particular, I have sketched here the Bode plot of our open loop system. We note that our omega gc can be obtained if we have specified the rise time and the damping coefficient as omega gc equal to omega n square root of 1 minus 2 zeta square, and the phase margin, which is the difference between minus pi and the phase of the plant, to be related to zeta as phase margin is equal to zeta times 100 when the phase margin is represented in degrees, or is approximately equal to 2 times zeta when the phase margin is represented in radians. And Finally, our steady state error specification ESS helps us to determine the necessary gain for our open loop system in the vicinity of omega equal to 0, and that gain has to be equal to 1 by ESS minus 1. This is in linear scale. To represent it in the Bode plot, it has to be 20 log of magnitude of 1 by ESS minus 1. So, we have now successfully transferred the closed loop frequency domain specifications into corresponding open loop frequency domain specifications, and if you notice here, we have made approximations all along from time domain to closed loop frequency domain and from closed loop frequency domain to open loop frequency domain conversions. Therefore, when we do the design using Bode plots, it is imperative for us to convert the designed open loop transfer function into the corresponding closed loop transfer function to see if our closed loop frequency domain specs have been met correctly, and subsequently to plot the step response of our closed loop system and see whether the time domain specifications have been met by the designed closed loop transfer function. We shall in the next clip take a look at a few standard controllers that will allow us to design our open loop system to meet the specifications of the kind that we have outlined in this clip. Thank you.